Hi everyone, we're rocking along and this is the fifth video tutorial, t-tests in SPSS, which is part of topic 6, comparing two means. In these two videos, we will specify null and alternative hypotheses, which is something you have some practice with by now. We'll check assumptions in SPSS using the explore command. We'll conduct appropriate parametric t-tests in SPSS, and we'll report the results in APA style. Part 1 covers independent samples t-tests. To complete Part 1, you need to have SPSS up and running. You need your pink book, and this is covered in Chapter 5. You need the data files data_5_1 and data_5_2 from the pink book companion website or from the folder that is posted on the Topic 6 Moodle page, or you need to be prepared to enter those data manually. All right. So if you're ready to enter data manually or to open data_5_1 in SPSS, let's get started.
Independent samples t-tests. So independent samples t-tests test whether the means of two independent unrelated samples are different. So we're comparing means of two different groups. They're based on the two sample means. The independent samples t-test is the parametric equivalent of a Mann-Whitney U-test, which we covered back in topic 4. And we'll talk about this more in lecture, but it's just like calculating a z-score, except we're using the t-distribution to adjust because we need to be more conservative because we're estimating the population standard deviation rather than using some known population standard deviation because we don't know what the population standard deviation is. The first example that we're going to cover for independent samples t-tests is based on a hypothetical replication of a famous false memory experiment. So in 1974, Loftus and Palmer published a study where they had investigated the effects of asking leading questions on memory reconstruction. So if you look at table 5.1, this is a replication that was done for a class project. The researchers, who are students, showed participants in their study videos of a car accident, and if you want to see the type of video that Loftus and Palmer used, you can find them pretty easily with a Google search for Loftus and Palmer car accident video. So these students replicated this study by showing participants videos of a car accident, and then they were asked either about how fast were the cars going when they hit each other, or about how fast were the cars going when they smashed into each other. So we've got two groups with 15 participants each, as you can see in table 5.1. And the only difference was whether the question involved the word hit or the words smashed into. So table 5.1 reports each participant's estimate of how fast the cars were going in kilometers per hour. You can see the fact that it's kilometers per hour up in the label for the table. So the heading for the table says speed estimates in kilometers per hour given by participants, n equals 30, so the sample size in response to either the hit question or the smashed question, and you can tell which is which by the organization of the table. So what I'd like you to do now is think about what in this case is the independent variable, what's the dependent variable, what's the research question, and I'd like you to formulate a null hypothesis and an alternative hypothesis. Okay, so on the next screen, I'd like you to pause the video while you do all of those things. So in this estimating speed example, the independent variable is the wording, right? Whether the researchers used the word hit or smashed into. So which group was the participant part of? This is a true experimentally manipulated independent variable as long as the researchers randomly assigned participants to the different groups. And the dependent variable is whatever they reported as the estimated speed in kilometers per hour. And that's a ratio scale variable, right? Because if the cars had not been moving or the participants had perceived that the cars were not moving, they would have reported a speed of 0 kilometers per hour. So we might ask the research question, do leading questions affect memory reconstruction? That's kind of our general question. We can make it more specific to this particular study by asking, do participants estimate different speeds when asked about cars that hit versus cars that smashed into each other? Now, I don't think the pink book refers to either of these groups as experimental versus control. Now, that makes sense because there's not really a principled rationale for calling one wording a control wording and another wording an experimental wording. So these are just two different groups, and it's an independent variable as long as participants were randomly assigned. And of course, the null hypothesis in this case would be that estimated speed was the same regardless of what wording was used when researchers asked their questions. So you might operationalize that by hypothesizing that the group mean for the hit group and the group mean for the smashed group would be the same. Okay, and our alternative hypothesis would be that the estimated speed was different when the question used the word hit versus when the question used the word smashed into. So our group mean for the hit group is not equal to the group mean for the smashed group. So that's a two-tailed hypothesis. We'd be interested in a difference regardless of the direction. All right, so if you're ready to set up your SPSS file, let's go to SPSS. So here's my data_1_5.sav file. I'm just going to double click on it, which will pull up SPSS eventually. Now I'm going to go to variable view. If you want to type in the data from page 48 manually or from the slides that are provided on Moodle, what I'd like you to do is set up 3 variables. One for participant ID, that is just the participant's identification number. Now this variable is used to keep track of participants. We're not going to include it in any statistical analyses. So we're not including ID in statistical analyses. I recommend that you have 0 decimals for that and you just include integers. And you might want a label that says something like participant number or participant ID. You don't need any values and you don't need to change anything else, and this is a nominal scale variable. The group variable is your independent variable. So this is used to specify whether the participant was asked about hitting or smashing into. It's also a nominal variable, but because the different numbers mean something other than just this is a different participant, we need value labels. So you might want to assign a label, something like experimental group or experimental condition or assigned question or something like that. And then in the values column, specify value labels, and the way that the pink book has the data file set up, they used the value label 1 for the hit question and the value label 2 for the smashed question. Your third variable is going to be speed. That's the dependent variable. So these are the participant speed estimates in kilometers per hour. So the label says speed estimate. You might want to add the units, so kilometers per hour in the label. This is a ratio scale variable, so we don't need to add any value labels. Okay, before we can conduct our t-test, we want to check the assumptions of the independent samples t-test. And the way the pink book describes it, there are 4 assumptions. That first one, scale of measurement, So the dependent variable should be interval or ratio data. There's not really consensus among psychologists about when or whether ordinal scale measures can be assessed using parametric tests. Certainly, there's no controversy that as long as the other assumptions are satisfied, are not violated, with interval and ratio scale variables, you can. And this is a ratio scale variable, so we don't need to worry about the lack of consensus. It doesn't apply to our dependent variable in this case. The assumption of independence of observations is that each participant should participate only once in the research and not influence the participation of others. As before, we can't assess this in SPSS. It's a design issue. The assumption of normality is that each of the group's scores should be drawn from a normal distribution. And the way we assess that is we look at whether the sample is roughly normally distributed. Now, I'm going to do something that's a little bit different than what the pink book is doing, very slightly. I'm going to use the QQ plots in SPSS in addition to the histograms. So the buttons that you click are the same buttons as specified on page 50 to 51. The assumption of homogeneity of variance is that the variances or the standard deviations of your two samples or your samples for the hit group and the smashed group are approximately equal. Now, we don't need to do anything extra to assess that assumption. The assumption of homogeneity of variance is tested as part of the independent samples t-test itself. Right, so looking at these data, I'm going to explore the estimated speed variable. So to do that, I click Analyze, and then Descriptive Statistics, which is the second option down, and then Explore, the third option down. We've done this a few times now. Speed is our dependent variable, so we want to move speed to the dependent list. We want to move experimental group to the factor list because we want information separate for the hit group and the smashed into group. All right, now we're not going to ask for any non-default statistics, but we are going to choose some non-default options under plots. So click the plot button, and in the Explore Plots dialog box, you can either uncheck the stem and leaf plots if you don't want to have to scroll past them, or you can leave them checked if you want to take a look at them. But you probably also want to look at the histograms. We do want to do normality plots with tests. So let's continue. And just as a reminder, we don't want to change anything about options. Excluding cases listwise means that if you had any missing data, then you wouldn't analyze any aspect of it. So if we were looking at, say, 3 or 4 different variables, if a participant had missing data for one of those variables, then SPSS would exclude that participant from these analyses altogether. Right? So again, just make sure the default option for display, which is both statistics and plots, is checked. Click OK. And as always with Explorer, we get quite a bit of output. So the case processing summary shows how many cases were analyzed and how many were dropped due to missing data. We didn't have any missing data, so all 15 participants from each group were included in these analyses. The descriptives table, if we scroll down a little bit, shows a whole bunch of data, some descriptive statistics, so a couple measures of central tendency and dispersion, also some descriptive measures of skewness and kurtosis that we're not going to particularly look at. The descriptives that we're interested in probably are the mean and standard deviation. If we've got normally distributed data, we're going to be looking at those in the output for the t-test itself. So what I want to call your attention to right now are the confidence intervals. So you'll notice in the near the very top, we've got a mean estimate of speed for the group where we use the word hit of 34.07 kilometers per hour with a 95% confidence interval around the mean of 32.57 to 35.57. So plausible estimates of between about 32.5 to about 35.5. And then if we look down at the smashed group, the 95% confidence interval is a little bit different. So 39.27 kilometers per hour to 44.06 kilometers per hour. And what you might notice is that those confidence intervals don't overlap at all. So the highest plausible estimate of mean speed for the participants who were asked about the cars when they hit each other is still lower than the lowest plausible estimate of mean speed for the smashed group, which is a clue that we can expect that we're probably going to get statistically significant results when we analyze using an independent samples t-test. But before we can do that, we need to assess whether our data are normally distributed. I want to caution against over-reliance on statistical tests of normality. Reason being, with large samples, you can get violations, that is a statistically significant result, when you don't have a meaningful violation, right? If you've got very large samples, those statistical violations are not meaningful. When you have very small samples, statistically significant violations should be interpreted with caution because you might draw a non-normal sample from a normal population. So you have to be a little bit thoughtful about it. However, when you have non-significant results, when your Kolmogorov-Smirnov tests and your Shapiro-Wilks tests tell you that your data are normal, you can be pretty confident that your data are normally distributed. And that happens to be the case here. We don't have any violations of normality as suggested by either the KS or the SW tests. Now, looking at the histograms, you might not necessarily conclude that these data are normally distributed, particularly the histogram for the smashed group. However, the KS and SW tests both say that these are normally distributed, and so we can be pretty confident that they are in fact normally distributed. That's why I like the QQ plots a little bit better than the histograms. So here's the QQ plot for estimated speed. The data points all cluster pretty close to the line, so I'm very confident that the hit group sample is normally distributed. With the smashed group, I see a couple deviations that are maybe a little bit larger than the deviations in the speed group, and you can tell this is sort of reflected in the kind of bimodal distribution of the histogram, but those are still pretty small. So I would be very confident saying that both of these samples are sufficiently normally distributed. Okay, which means that we can proceed with our independent samples t-test in SPSS. Right, so to conduct an independent samples t-test in SPSS, I'm going to click Analyze. I want to move 1, 2, 3, 4 options down to compare means. And then I'm going to choose independent samples t-test to conduct an independent samples t-test. So that's pretty straightforward. In this dialog box, I need to specify the test variable. That's my dependent variable. And note that if you wanted to conduct a whole bunch of t-tests on different dependent variables at the same time, you could move multiple dependent variables into that test variables box. We're only going to look at the one dependent variable that we have. Then we need to specify a grouping variable. So I'm going to select experimental group, move that there. You'll notice that I can't click OK even if I want to at this point. So I've put my independent variable in the grouping variable, and the next thing that I need to do is define groups. So I click on define groups, and I get this little dialog box. We're going to use specified groups. Remember that we specified that a value of 1 in our group variable meant the participant was asked the question about cars hitting each other, and a value of 2 meant participants were asked the question about smashing into each other. So that's all we need to do for defining groups, is put our group assignments, the numbers that we assigned to each of those groups, into group 1 and group 2. Right? Just to show you, you don't actually have that many options. If you wanted to look at a different confidence interval, maybe 80% instead of 95% or something like that, you could do that. And if you're conducting multiple t-tests and let's say you had some missing data and you wanted to include as many subjects as possible, so you'd only exclude participants from analysis if they actually had missing data for the dependent variable that you are analyzing, then you would exclude cases analysis by analysis. If you want to exclude Gestalt, so if there's one missing data point, then you don't include that participant in any of the t-tests, then you exclude cases listwise. We don't have any missing data and we're only doing one t-test, so those missing values are totally irrelevant for us. So that's all there is to it. So here we are, we've specified our dependent variable, that test variable, the estimate of speed. We've specified our independent variable, the grouping variable, group hit versus group smashed. We defined our groups so that we know which number goes with what group. We're ready to click OK. When you conduct an independent samples t-test in SPSS, you get 2 tables as output. First table shows you group statistics. Those are descriptive statistics for each group, right? We've got sample size, mean, standard deviation. We've also got standard error of the mean. And then we've basically got 2 versions of our test statistic. So here we are back in PowerPoint. So that first table with the descriptive statistics tells us that the estimated speed for the hit group was lower than for the smashed group, so our mean estimate of speed was higher for smashed. Now in the second table, the independent samples test table, you'll notice that the first set of results, the first 2 columns of results, report the Levene's test for equality of variances. You might remember that that is the test that we use to assess the assumption of homogeneity of variance. If we have a significant Levene's test, we conclude that the variances are heterogeneous, and then we have to deal with that. But you might also remember reading, or you might remember hearing me say that when you've got equal sample sizes, violations of homogeneity of variance are not as important. Well, in this case, we've got a relatively small F ratio, 2.486, and our significance level, our p-value, is greater than 0.05. So we can conclude based on the Levene's test that the variances are homogeneous, so that assumption of homogeneity of variance is valid. If a Levene's test indicates that you can't assume equal variances, so if it indicates heterogeneous variances, you can use what's called a Welch's t-test. What Welch does is a mathematical correction to the degrees of freedom that reports lower degrees of freedom which means you have a higher critical value, so it's harder or less likely to produce a statistically significant result. So that's all that is, but we don't need to worry about that in this case. We can assume equal variances. So that means that what we should pay attention to are the numbers in the first column of that first row of that second table rather than the second row. So we've got a t-score of negative 5.77, 28 degrees of freedom. Remember, we've got 15 participants in each group. We're calculating one mean and one standard deviation. We've got one calculation for each group. So we lose a degree of freedom for the hit group, and then we lose another degree of freedom for the smash group. So of those 30 observations, we have 28 degrees of freedom. Our p-value, that two-tailed significance, remember we did a two-tailed test, is not going to be equal to 0 because you never get a p-value of exactly 0. But what that tells us, what that 0.000 there tells us, is that the p-value is something less than 0.001, because if it was 0.001, it would say so. So in APA style, we're not really interested in very, very tiny p-values. So if you've got 0.000 in your SPSS output, you would just report in APA style p less than 0.001. Now, the rest of the columns there report the mean difference. So that's, you'll notice, if you subtract 41.67 minus 34.07, so if you take the smashed mean minus the hit mean, you should get 7.6, which is what's reported in the independent samples t-test table. We've also got a standard error on the difference and 95% confidence interval on the difference scores. Now that minus 10.298 as a lower limit and minus 4.902 as an upper limit, you'll notice that that doesn't include 0. The way we would interpret that is that a plausible true difference between the hit group and the smash group is about minus 0.5 to, or minus 5 to minus 10. So meaning our range of plausible estimates is that the smashed group reported speeds between 5 and 10 kilometers faster than the hit group. Okay, so we've got a statistically significant difference. Now we want to do some follow-up analyses and report effect sizes. Your textbook and the pink book don't talk about this, but that non-standardized difference, that difference of 7.6 kilometers per hour in the independent samples t-test second table, that is an effect size. So we can conclude that speed estimates were 7.6 kilometers per hour faster for the smash group than the hit group. It's also good practice to report a standardized effect size. And Cohen's d is the effect size that answers the question, how many standard deviations apart are the two means? But now we have a problem because we've got two standard deviations. So which standard deviation do we use? Well, we've concluded that the two standard deviations are not really that we're not statistically significantly different. So some people will say, well, just use the larger one because that gives you a smaller effect size. And that's not a wrong thing to do, but the more standard thing to do is to just pool the two standard deviations. So basically calculate an average standard deviation. But because we've got square roots and squaring and things like that, the arithmetic of calculating an average standard deviation gets a little bit more complicated. So I encourage you, I've written this out in multiple steps. If you like, pause the video if you want to work this out for yourself. Basically, the numerator is degrees of freedom times the sample variance for sample 1 plus the degrees of freedom times the sample variance for sample 2. And then the denominator is our total degrees of freedom. So we've got 15 minus 1 times the standard deviation for sample 1, and then we have to square it because we're looking at variances, plus 15 minus 1 sample size for sample 2, they're both 15s, times the variance for sample 2, so we've got to square that standard deviation. So I've plugged all the numbers in, done the arithmetic, and when you get down to this second last line, we're looking at 14 times 7.355, which is the variance for sample 1, plus 14 times 18.662, the variance for sample 2, divided by 28. So just as a note, remember we're taking these numbers from the group statistics table, the descriptive statistics table. We've got to square them because we want the variance. Note, we're looking for S squared, not S. We've got to divide by our degrees of freedom. And then because we've been dealing with variances and what we want is a standard deviation, we've got to take the square root. So what we end up with is, square root of 13.009, which is 3.607. Now you might notice that in my calculations, the third and even the second decimal places are a little bit different than what's on page 55 of the pink book. That's just rounding error, and as you can see, it doesn't produce different results because we both end up with 3.607. Okay, so we've got a pooled standard deviation. We still don't have an effect size. So what we're asking is how many standard deviations apart are the two means? So basically we're standardizing the mean difference. We're calculating the difference between the two means and then dividing it by our estimate of pooled standard deviation. Well, we got that difference between the two means from the t-test table, or you can just subtract 41.67 minus 34.07 and then divide by the value we just calculated. So we get 7.6 divided by 3.607, which is approximately equal to 2.11. And the way to interpret that is that the smashed mean is more than 2 pooled standard deviations above the hit mean. And as it says in the pink book, there are some great easy to use online calculators for computing effect size. So if you don't want to pull out your calculator and estimate the pooled standard deviation, one of the ones that I like is this danielsoper.com statistics calculator. He's got a whole bunch of statistics calculators on this web page, but if you navigate to that using the hyperlink in the slides, or you are welcome to type that in yourself, then you can just put in the means and standard deviations for the two groups, and all of the arithmetic we just did, there's an online tool that will do it for you. Okay, so the next step is to write these results up in APA style. You can look at the APA style results right up on page 56 for a model if you like, or use some of the models in chapter 9 of the textbook. Give it a go, and then we'll compare notes when you're done. All right, so my results section that I've written is a little bit different than the way that the pink book writes it up. They're both wordier than you might see in a journal article, but that's okay. There's not one correct way to write this up. But I do want to point out a couple of things. All of the underlined details there are descriptive statistics. So I've reported the means and standard deviations for each sample, for the hit group and for the smashed group. And note that I've reported the units, kmph, kilometers. Km is a standard unit in APA style, but somewhere I would probably want to specify somewhere in my article that when I use kmph, what I mean is kilometers per hour. You can find the common abbreviations for units of measurement in table 4.4 of your APA 6th guide. That's on page 109. So the words that I have outlined in these gray boxes, these two sentences are related to assumption testing, right? I've reported that visual inspection of quantile plots for the hit group and the smash group indicated speeds for both groups were approximately normally distributed, and a Levine's test on sample variances was not statistically significant. Even though it was not statistically significant, I've reported the F ratio with the degrees of freedom. In this case, that F ratio is going to have 1 and 28 degrees of freedom, so it has 2. So you write 1, comma, and then however many degrees of freedom the equal variances assumed t-test has. However, all of those statements, those two sentences outlined in gray, are ones that I would probably leave out of a journal article. For lab reports and things like that, your markers are going to want to see some confirmation that you actually did do the assumption checks that you were meant to do. We trust people who are relatively experienced, but in order to get to that point, you have to confirm that you have done the tests. So that's why it's good practice for you to include that kind of detail. All right, next. The new underlines. Written a two-tailed independent samples t-test for homogeneous variances, so I'm giving the reader a lot of detail about what kind of test it was. It was a t-test. It's an independent samples t-test. It's got two tails. It wasn't a one-tailed test. And homogeneous variances were assumed. Again, that's probably a little bit redundant because we've just reported the Levine's test result, but it can't hurt to specify. Right? Then I've said they revealed that speed estimates for the hit group were significantly lower than those of the smashed group. And there are the relevant numbers. The t equals, and then in parentheses, the number of degrees of freedom. Remember, there were 30 observations, so 28 degrees of freedom. The specific t-score, the p-value, and then the effect size. But you'll notice that I also reported the non-standardized effect size a little bit earlier in the document. Okay, so that's a lot of words to basically say that estimates were affected by wording. All right, if you haven't done so, I recommend that you save your output file with a memorable file name so that you can come back to it. You probably haven't modified your data file, so you don't have to modify it. You don't have to save that if you don't want, but it can't hurt to do so. All right, in the first example, the independent samples t-test we conducted was statistically significant. All of our assumptions were valid, and we had a fairly large effect size. However, you can't count on all of that happening in real life. So we're going to look at another example where not all of those things are the case. So here in our second example, as part of a national assessment program, the students in Miss Summers' Year 7 class completed an intelligence test. Their global IQ scores were tabulated, and they're shown in table 5.2 on page 57 of the Pink Book. Mrs. Summers would like to know whether there's a difference between the average IQ of her male students and those of her female students. Right, so what is Mrs. Summers' research question? What's her null hypothesis and her alternative hypothesis? And it might help you to think about what are the independent and dependent variables. Okay, welcome back. So we don't actually have an independent variable in the sense of a true manipulated experimental independent variable, right? The predictor variable that we're going to use is sex, male versus female. Right? That's not a real experimental independent variable. That's what is sometimes called a subject variable and what field would call a predictor variable because that's the way that we're grouping our observations to evaluate them. And our dependent variable is intelligence as operationalized based on the global IQ score. So our research question is something like, are there differences in IQ of Mrs. Summers' male and female students? The null hypothesis would be that there's no difference. And the alternative hypothesis is that there is a difference, that the mean IQ for males is not equal to the mean IQ for females. So we've got a two-tailed hypothesis again. Right, and we check the same assumptions as we did for example 1. We don't need to worry about scale of measurement. Like I said, there's some controversy over whether you might use IQ score in the same way that you'd use interval or ratio scale variables because it's technically an ordinal scale measure, but it's well validated that IQ scores behave like interval ratio scale variables. So most psychologists treat IQ as the same way as interval and ratio scale variables. That is, they conduct parametric tests with them. Now, having said that, you wouldn't be wrong to use a non-parametric test on something like IQ for the reason that it is an ordinal scale measure. It's just not something that most psychologists do, but that doesn't mean that it's a wrong thing to do. Again, independence of observations is not something we can assess in SPSS. To assess normality, and you can see I've got some graphs here, we're going to explore the data. So let's go to SPSS. So data underscore 5 underscore 2.sav has 3 variables, just like before. First thing we're going to do is analyze, click descriptive statistics, and then explore. We're going to use IQ as our dependent list. Oh, and I hadn't realized gender is coded as a scale variable. It's not going to change any of our analyses, so I wouldn't worry about the scale of measurement for our predictor variable that we put in the factor list. This will give us separate results for males and females. We don't want to change anything about the statistics, so I'll just click continue. But I'm next going to click on plots. I do want to see the histograms. If you want to deselect stem and leaf plots, we're probably not going to look at them. And I want to see normality plots with tests. I'm more interested in those QQ plots than with the tests, but SPSS, if you ask for one, it gives you both. So there we go. And we want to see both statistics and plots, and OK. So here we have our case processing summary. Note we've got different sample sizes. This is something that education systems, it's not always possible to have the same number of males and females assigned to each and every classroom. And in fact, you might not even get them as close as they are in this case. We've also got descriptive statistics, just like before. You can see males have a mean IQ of 104.61 with a 95% confidence interval of about 99.3 to 109.9. Females have a mean IQ of 103.82 with a 95% confidence interval of 101 to 106.6. So right away I can tell that there's a difference in how variable males and females are. Whether that's a statistically significant difference, I don't know. Now, if we look at tests of normality, we can see an absence of violations of normality based on the Kolmogorov, Smirnov, and Shapiro-Wilks tests. So you can get something that does not look normally distributed, but in fact is as normally distributed as you might expect for a small sample size. Okay, and here are our QQ plots. Again, it looks to me like the male distribution is more normal than the female distribution, but we wouldn't conclude there's a violation of normality in either case. So we've checked whether the distributions are normal, and they do seem to be, which means that we can go on and conduct our independent samples test in SPSS. So just like last time, analyze, compare means, independent samples t-test, and I'm going to click the button. That brings up this independent samples t-test dialog. Again, IQ is my test variable. Gender is the grouping variable. We've still got to define groups. Remember, we have 1 for males and 2 for females. I'm going to click OK, which gets me those same 2 tables. Okay, so one thing we can tell from that top table with the descriptive statistics is that the mean for males is a little bit higher. Not drastically, less than 1 whole IQ point higher, but it is a little bit higher for males. You might also note that the standard deviation for males looks to be about double the standard deviation for females. From the Levine's test, we've got an F ratio of 5.689 and a p-value of 0.023, so that's less than 0.05. So we would conclude that the assumption of homogeneity of variance has been violated. We have heterogeneous variance, right? Which makes sense that standard deviation is for males is about double the standard deviation for females. They're not even approximately equal. And the way we can tell that statistically is the violation of the Levine's test. Now, that doesn't mean we're done. That doesn't mean we can't report the results. What it does mean is that we're going to use the second line, the second row in the independent samples t-test table as opposed to the first one. Now you'll recall that I said that the Welch t-test as compared to the standard parametric students t-test just corrects the degrees of freedom downward a little bit to accommodate the violation, sort of to balance or correct for the violation of the assumption of homogeneity of variance. So we're treating this test as if it has fewer degrees of freedom than it really has. So if they'd had similar variances, because there are 18 and 17 observations, we would have a total of 33 degrees of freedom. But instead, we have only 25.485. Now that's a clue that you've done some kind of modification anytime you're reporting a non-integer number of degrees of freedom. And notice that our t-score has also changed just a little bit. And also notice that the p-value for the t-test is not statistically significant. And that would have been true if we'd assumed equal variances. It's true since we don't assume equal variances. Those numbers differ only in a very tiny amount. So the mean difference is the same regardless whether you assume equal variances or not. The standard error is a little bit different, and because the standard error is a little bit different, the 95% confidence intervals are a little bit different. Now, just like last time, we can calculate a non-standardized effect size. That's that mean difference. The average male IQ was 0.79 points higher than the average female IQ, and there I've reported the 95% confidence interval that comes from that second row of the t-test table. And now let's use the link from before on danielsoper.com to calculate our effect size. So when we go to this link, we get a bunch of ads, and we also get spots to type in our group means and our group standard deviations. So you can read from your SPSS output from that first table, a group mean of 104.61 for males, 103.82 for females, and then for males we've got a standard deviation of 10.639, and for females 5.376. So this is just so that we don't have to do all of that arithmetic ourselves. We'll click calculate, then there's a little bit of JavaScript or something that does the calculation for us. And our effect size is 0.0937, etc., etc. So we don't calculate a different type of effect size because we have heterogeneous variances. That Cohen's d calculation is the same. Okay, last thing I want you to do for part 1 of this video is to write up your results in APA style. So I want to recommend that you do it without looking at page 60 as a model. Try and do based on what we talked about earlier in the video for the first example. See if you can write up these results on your own. Okay, here are my results. They might be a little bit different than yours. So IQ tests were administered to compare intelligence of year 7 males and females. Visual inspection of quantile plots. So here I am describing assumptions. Indicated IQs were normally distributed for males, and I'm sneaking in my descriptive statistics into this sentence by reporting in parentheses the mean and standard deviation, and notice that M for mean is italicized and SD for standard deviation is italicized. And females, I've done the same thing. So visual inspection of quantile plots indicated IQs were normally distributed for males and females. However, Levine's test on sample variances was statistically significant. And now here, no matter what, you would want to report your F ratio. And just like last time, we've got one numerator degree of freedom. We've got 2 degrees of freedom. So the first one is always 1 when we're doing t-tests. And the second one is however many degrees of freedom we have for our equal variances assumed t-score. So 1 in 33 equals 5.69, and we've reported the exact p-value. And there's a stray parenthesis that doesn't belong there. And then I've interpreted that for the reader. So indicating heterogeneous variances for males and females. As a result of that heterogeneous variance, we're reporting that a Welch's independent samples t-test for heterogeneous variances. So just in case you don't know what a Welch's independent samples t-test is, I'm telling you it's a t-test for heterogeneous variances. Indicated that differences in IQ between male and female students were not, and I should probably say not statistically significant. And then I've reported my t-score, that funny degrees of freedom. Remember, we corrected that down. The t-score is really low here, and the p-value is quite high. And the effect size is very small. So that all together would lead us to conclude that there's not really any there. That this is pretty compelling evidence that the null hypothesis is the one that is supported by our data. All right, now that's all the work for part 1. If you have not done so, now's a good time to save your output file and your input file, your data file, if you modified it with memorable names so you come back to it. And I will see you a little bit later when you choose to do part 2. Bye for now.